In this course, we will talk mainly of two types of waves, what we call transverse wave and longitudinal wave. In the case of the transverse wave, the medium of the wave, for example, if we have a rope, like in this case, the medium would be the material of the rope, oscillates perpendicular to the direction the wave is moving. For instance, here, the wave is moving horizontally from left to right, as we see the wavelength here moving, but then the medium, these black and red dots, are oscillating just up and down. Pay attention, for example, to the red dots, and you'll notice that, like the red dot, it's going up and down about this point here. This red dot is going up and down about this point. So the actual medium is not traveling. The wave is traveling towards the right, but the medium is just oscillating perpendicular to the direction of motion of the wave in that same position. Examples of transverse waves, water waves like ocean waves more or less look like transverse waves. We can see later on a demo with a slinky where we will see a transverse wave. There are many examples of transverse waves. You'll see later on, for example, that electromagnetic waves are transverse waves. Longitudinal waves, on the other hand, are waves where the medium oscillates in the same direction as the wave is moving. For example, here we are producing a sound wave by compressing and stretching the air. Compressing the air, expanding it. Compressing it, expanding it. That's the way a speaker, for example, works. And by doing that, the actual wave is going to move in the forward direction, from left to right, like for this wave here. And here we are representing the pressure of the sound wave, the pressure of the air inside here. You notice that the pressure is going to look very much like a transverse wave, where we have maximum compression of the air, that's maximum pressure, so we see a crest, and where we have maximum expansion of the air, that's low pressure, we see a trough. So it's moving in the forward direction. But the medium itself, and pay attention to the red dots again, is going to oscillate back and forth in position. It does not move forward with the wave. It just oscillates in the same direction. Like the red dot here, it's oscillating back and forth here. But it does not move forward. Similarly, this red dot or this red dot. Examples of longitudinal waves, sound waves, and then we'll look at other examples with a slinky, which is a type of a spring. Which brings us to this. So what we are saying, for a longitudinal wave, which we also call compressional wave because of the way we compress the medium. In this case, we take the example of a spring. You see here is a representation of a spring, and then we compress the spring. We compress the coils of the spring. Now, when we compress the coils of the spring, we are going to store spring potential energy here. That spring potential energy is what actually is going to travel along the spring. That's really a representation of the wave or the wave energy. For a longitudinal wave, the medium, in this case the spring coils, move in the same direction, so they're going to oscillate back and forth in the same direction as the direction of travel of the energy, which is the compression part here of the spring. So the medium is going to oscillate back and forth horizontally, while the energy is going to move forward in the forward direction. Okay. Now another way to look at this, or just to make sure we understand all components involved here, when we have a transverse wave that looks somewhat like this, what we call the amplitude is how much the medium is going to oscillate about equilibrium, which is the height of a crest, or the depth of a trough. That's what we call the amplitude. The amplitude is a measure of the amount of energy that the wave is going to carry. Now, what we call the wavelength is the distance from crest to crest, or trough to trough, or any point on the wave to an identical point on the wave. So it's just the length of the wave, of a single wave. For a longitudinal wave, we are also going to have an amplitude, but in this case, it's going to be represented by how much the medium is compressed. In this case, we see a spring. The amount by which the spring is compressed is measuring for us the amplitude. The amount by which it is stretched is also going to measure for us the amplitude. The amount of stretching and compression, you are familiar with it with the spring, 1/2 of kx squared. So that's the amount, that's a measure of the energy stored in the wave. The wavelength, of course, is going to be the length of a wave, so it's from a maximum compression to a maximum compression, or a maximum amount of stretching to a maximum amount of stretching. Notice here, the crest corresponds to a maximum of a compression. The trough is corresponding to a maximum amount of stretching.